there are three different perspectives on regularization, which correspond to the three components of machine learning. So you can regularize via the data set, you can regularize via the model, and you can regularize a method via the loss function. So let's look at the basic training problem for linear regression as our prototype of a machine learning method. So we want to minimize the squared error loss, average squared error loss on a training set. Okay. So let's say this overfits. We have in the extreme case, so let's say the extreme case, we have only one data point and 10,000 features of a data point. This might sound a bit ridiculous, but this might actually reflect how machine learning is applied in practice. You have a data point being me, Alex, with billions of features, like I now bought maybe some of you have also a polar heart rate sensor, and every time I do training, I get a time series on a minute interval heart rate measurements. So tons of features, but only one data point. So how can I learn a useful model only for one data point with so many features? Well, what we could do is we could increase the number of data points by perturbing a bit the original data point. This is called augmentation, data augmentation. So we add a bit of noise to the features, and we can draw as many random variables or realizations of a random variable as we want. So we can do a billion times. And we just get always different, slightly different features, but leave the label untouched. We could also perturb the labels by adding a bit of noise. Okay, let's say we do this with a standard deviation called square root of alpha. There's a certain reason why I call this square root of alpha, as we will see later. And we then do, we add kind of here this additional terms, these error terms on the augmented data points. So let's call this augmented data point x10 and y10. So for each augmented data point, we get an additional error term in the training error. Y10 minus W transposed x10 squared. And you can increase M as large as you want, as many realizations you draw. So this is called data augmentation. This is one form of regularization. Another form comes naturally out of this process because you can collect these additional terms into a single term. If you say you generate these perturbations, so this call this perturbation here epsilon from a Gaussian distribution with a certain variance. Then it turns out this sum here converges to via which law? Which law can we use to replace a sum of many terms with something easier? Which law have we heard about just before? The law of large numbers. Again, so we have here a sum over many realizations, and this becomes an expectation of a random variable, and it turns out this is calculated in the lecture notes. This becomes the noise variance times the weight vector squared. All these additional terms. So what we see is data augmentation with a large number, infinitely many perturbations, becomes equivalent to minimizing the average squared error loss on the original training set, plus another term which corresponds to all these additional error terms on the augmentations, on the augmented data points, which is sigma squared times W norm squared. Did any one of you see such an optimization problem or know how this machine learning method is called? Yeah.
That's rich regression.
Very good. That's called rich regression. How many of you have heard about rich regression before? Very good. And how many knew that this is equivalent to data augmentation? Very good. So I have something new for you still. Rich regression. And this is nice conceptually for me. I find this nice because I was always struggling with interpreting this term. I was teaching rich regression for a while, and I was always wondering how should I best explain this additional term. And one interpretation of this additional term is that it's all these additional error terms, squared error terms that come from these perturbations. And when you do this infinitely many times, these additional error terms here become the expectation of a random variable. And when you work out this expectation, you get exactly this penalty term of rich regression. And this also shows you the role of the parameter, of the rich parameter. It's a noise variance. So the larger this a rich parameter is, which is called alpha, for example, in Python, the larger is the noise variance that you use for these perturbations. Okay, so now I told you how to do regularization via data by augmenting data points, adding more noisy versions of the original data points. And I have showed that this is essentially equivalent to adding a penalty term to the loss function. So we have basically modified the squared error loss by adding this additional term to the loss. So what's the third perspective then of regularization? Sorry? Model, yeah. So how is this related to model? Well, it turns out that if we write this down, minimizing this training error term plus sigma squared lambda 2 has a special structure. Who of you took a course on optimization or convex optimization? Okay, so this might be something new for many of you, or maybe just a refresher. This could be interpreted as a Lagrangian term for a constraint. So this is equivalent to minimizing the what we had here, the training error. So let's write it out, yr minus w transposed xr squared. And this term here, this penalty term in the objective function, becomes a constraint, becomes w squared. So this function here, smaller or equal than some number eta, and the eta is related to the sigma squared. It's not very easy, very trivial relation in general, but you can work out for a given sigma squared what would be the eta and vice versa. And this relation or this equivalence, this is called Lagrangian duality. This is a core of many convex optimization courses. So I highly recommend, if you have time, to take one of those courses by, I think the electrical engineering department offers them. So Lagrangian duality allows you to find out that minimizing this penalized training error, rich regression, is essentially equivalent to training a linear model, but training a subset of all possible linear maps, in particular the subset of linear maps whose weight vectors satisfy this constraint. Okay, so now I have shown you basically 3 equivalent ways to regularize linear regression. One is by adding more perturbed data points, data augmentation, which is equivalent in the limit of using many perturbations to adding the penalty term in rich regression, which via Lagrangian duality is equivalent to pruning the hypothesis space to make the model smaller.